Let's go through a one sample t-test from beginning to end. So let's say you had a question. You wonder if the expectation of good weather, you see the weather forecast and it's going to be sunny tomorrow or whatever you consider good weather. Does that affect how generous you are or how someone else is? Interesting question. So how would you test this? Well, first of all, what would the null hypothesis be? Null hypothesis would be that no, um, the expectation of good weather doesn't affect a level of generosity. Alternative would be that it does. Maybe it increases it, maybe it decreases it. This is a two-tailed alternative. We're not quite sure which direction it would go. So they actually did a study on this. It was in, I believe, California, somewhere on the West Coast, at this restaurant, and they were curious about this particular concept, this topic. And so what they did is they chose a random sample of customers, and the waitress would write a little smiley face and say, "Looks like good weather tomorrow!" Exclamation point or something like that. And then they would see what percent of the bill this particular person tipped. And the idea was that if people who got that message were impacted in some way, they might tip a different amount on average. And of course, they knew the standard amount of tipping at that restaurant already. So that was a known value. I believe it was 21%. So in general, pretty generous patrons at that restaurant, but 21% was the average tip. They want to know this expectation of good weather, whether it could potentially increase or maybe even decrease this 21% on average. So this is what they collected some data. Bunch of people, these are all ones who got that message of, now there is some deception here because I don't know that there was going to be good weather the next day or not. But this is how much each person tipped. Now, if you just flip through there, you notice that some are below 21 and some are above 21. So just off the bat, we can't really tell whether or not, we don't have an answer to our question yet. So we get the sample mean. There was 20 patrons here. We get the sample mean and find out it's 22.21. So on average, of the 20 people who got the good weather message, they tipped an average of 22.21%, which was higher than the 21%. But we can't say yet that in general, people who get this message would tip a higher amount. Right now, we just know that these 20 did. And that's what a null hypothesis test is doing. It could be that our particular sample of 20 just happens to be a really high tipping sample. And so that's why we conduct a t-test and see probability-wise if it really is true that, if it's true that the null hypothesis is right and expectation of good weather does not affect generosity, how strange or how unusual would it be to get a sample mean that's this far away from the null hypothesis mean? The null hypothesis mean being 21%. If it doesn't affect, if the good weather doesn't affect someone's generosity, then we would see an average, we would expect to see an average over the long term of people getting the message of tipping 21%, because null hypothesis says it doesn't affect their generosity. The alternative here is that the average will not be 21%. But just because we get a sample mean of 22.21, we can't yet tell whether or not this is far enough away from 21 to really be unusual, or maybe it's just by random chance alone, these 20 happen to be high tippers. So that's where we move down. We can look at the t-statistic, compare it to the critical t. You can think of the critical t as a cutoff, and the t-statistic needs to get beyond it in order to reject the null. But we're just going to focus on the p-value. So what happens here is the lower the p-value, the more unusual this type of situation would be if the null hypothesis were true. So in English, and as plain as we can get it, if the null hypothesis is true, if the expectation of good weather does not affect generosity whatsoever, then we would only have a 1% chance or a 1.2% chance of getting a sample mean this far away from that null hypothesis mean. In other words, it would be very unlikely. So the lower the p-value, the more evidence against the null. The catchy saying is, if if p-value is low, the null must go. So the lower the p-value, the more evidence there is against the null hypothesis. In general, we have kind of a cutoff of 0.05. That's our threshold. If our p-value gets below that threshold, that's called a level of significance. If the p-value gets lower than that, think of it doing the limbo or something, then we say we have a statistically significant result. So here we can see with this data, there is a statistical significant difference when someone expects good weather. And then we want to look at something called practical significance. So p-value tells us statistical significance, whether or not there probably is an effect or is a difference. It's kind of a yes or no thing. And then practical significance answers the question, how big is the difference? How much of a difference is there? Well, we can measure that with different ways. In regression, the r-squared helps us know practical significance. In a t-test, we often look at something called Cohen's d. And what this is how many standard deviations away from the mean, the null hypothesis mean, was our sample mean. So our sample mean was obviously far enough away that we had a statistically significant result. But how far away was it? It was 0.61 standard deviations, or 0.62 if we round that up, standard deviations away from the null hypothesis mean. The sample mean was 0.62 standard deviations away from the null hypothesis mean. Is this a big size? Well, yeah, we would typically say that 0.1, 0.2 is a low effect size for Cohen's d. Maybe 0.5-ish would be medium, so 0.4 to 0.6. 0.8 or above is typically a large effect size. It really depends on the context. These are just kind of very general rules of thumbs. But if I see a Cohen's d above 0.5, I tend to think, yeah, there's some substance here. There's some effect size here. And then confidence interval. So what this is saying is we can be 95, this is a 95% confidence interval. We can be 95% sure that if we were to collect many, many customers at this restaurant, giving them the sunshine message, that their tip level would be, on average, somewhere between 21.3 and 23.1. So notice, even in the worst case scenario, even on the lowest there, we're still higher than the existing average at that restaurant. That's because we do have a statistically significant result. But it could be that it's quite a bit higher too. So confidence interval also helps us, in a sense, get some picture of effect size of how big the difference probably is. So it's probably somewhere in that range. It's probably not like 25%, 30%, but it probably does give a little bit of an edge in terms of how much extra generosity. Okay, so what do we do there? We rejected the p-value, so p-value low, null must go. Sorry, we rejected the null hypothesis. P-value low, null must go. This is, we don't worry too much about the t thing there, but the p is less than 0.5, so we reject the null. And we can say that the fair weather messages probably do predict a higher tip at that restaurant. We could also use the confidence interval. These two are going to be consistent. So because the confidence interval told us that the average tip for the sunshine message would probably be between these two numbers, not just for that sample of 20, but in general, customers at that restaurant, then even in the worst case scenario, it's probably higher than 21%. Okay, let me